Good afternoon, and a very warm welcome to one and all present here. Hope you are having a great day and congratulations on your JEE advanced results. This 2 year JEE prep journey takes perseverance, and with this virtual education conclave by Techfest IIT Bombay, we wish to bring to you the information tools to satisfactorily conclude it by choosing upon a technical stream and college. So, guys, keep your questions handy. We'll be starting in a couple of minutes. So let's get started without any ado. My name is Kalash Shah, and I welcome you all to the first edition of Virtual Education Conclave conducted by Techfest IIT Bombay. Techfest IIT Bombay is Asia's largest science tech festival. And before you all become engineering students and come to attend it in person, let's have a look at a beautiful after movie that we have to present. Yeah. So, well, wasn't that a power packed and a tech packed after movie? For the information, guys, this was the after movie of the Techfest 2019-20 edition. Well, let's dive into the session now. And let me introduce to you the esteemed speaker for the third session of the first day. Today, we have with us Professor Arghya Deb. He is a professor of civil engineering and the Associate Dean of Infrastructure at IIT Kharagpur. Welcome, sir, and thank you for being a part of our education conclave. Handing it over to you.
Thank you very much, Kalash. And I want to thank the organizers of Techfest for inviting me to speak to your young audience here. My understanding is that you have a diverse group here. So I'm not really sure who are, but from the questions, I find that most of you are probably new entrants. You have just cleared the JEE Advanced, right? But anyway, my talk is going to focus on civil engineering as such. And if there are some civil engineers out there, maybe there will be some things of interest to you as well. But I'm not assuming that you have a background in civil engineering, right? So with that, let me start sharing my slides and let's go ahead. So I hope you can see my slides, right?
Sir, they aren't visible. Could you just share them once?
Okay. Is
Perfect.
it
They're
visible
visible.
now?
Yeah.
Oh, great. Okay. So the topic of my presentation today before you is civil engineering, basically a broad introduction to civil engineering with a focus on what I feel is where civil engineering is going to go in the next few decades, right? So the topic of the presentation is building a sustainable future. So civil engineers, what do? We basically build, right? That is our main occupation, right? So we build to serve human needs. And for a long time, we wanted to build better, right? So we were building all the time, but we wanted to build better. And somewhat more controversially, we wanted to build bigger, right? So that meant building taller buildings, bigger dams, roads with more lanes, and things like that, right? So building better buildings, better dams, better water supply systems, and better roads is still our major goal. However, now there are two additional concerns, right? One of them is how do we build sustainably, right? With the least impact on the environment, and how can we build more durably so that in the long run, we need to build less. So you might think that by doing that, we will be putting ourselves out of a job, right? Civil engineers won't have much to do, but as we will see later on, right, that is not exactly true. So in the first part of the talk, I will briefly describe some of the areas where achieving the above objectives is becoming more and more important. And once I do that, I will talk about things about which I have more first-hand knowledge because I teach about them and I do research in those areas. So that is how can we build with building materials which are more sustainable, right, and more versatile. And I will choose one particular building material, which is concrete, which is probably the world's most used building material, right? And I will talk in more detail about that. So civil engineering, what are the important challenges for the future? If you know anything about civil engineering, you know that civil engineering is a very diverse field. It's not just buildings, right? We build structures, and those structures can be all types of structures, even a space station, right? That is a structure, and I know civil engineers have had something to do with that as well, right? From underground tunnel to space station, anything you build, you have civil engineers involved in that. So in the future, what the structures that we want to build, right, there are three things we want to emphasize and which seem to be to me very important, right? Safer structures, as such structures should be safe, and as time passes, the nature of our hazards are changing, right? For instance, earthquake events, they were always there, but and then there are extreme weather events, right? Floods, right? So earthquakes, floods, and then nowadays there are structures are subject to terrorist attacks, right? Blast loads, right? So we need to build safer structures, and we need to build sustainable structures. So we need to build in such a way that we do now. It doesn't so happen that after some time we totally run out of building materials. We have nothing more to build, right? So we want to build sustainable structures, and we want to build with better materials so that we can do more with less, right? We can use lesser materials to build stiffer, stronger structures, right? So that's building structures is one major part of civil engineering. Then water, the second major concern is with water. And relieving water stress has become very, very important, particularly with climate change. As you know, with climate change, I think it is now well accepted that the frequency of droughts and floods are going to increase, right? So that is a major challenge for civil engineers, because if there's a shortage of water, civil engineers have to supply that water. If there is excessive rain, they have to design their water management systems in such a way that it causes the least damage. And in doing that, we have to build structures which are environmentally friendly. So environmentally friendly dams. If some of you read the newspapers, you must be aware that that there's been a lot of discussion in the media about the effect of large dams. How do they affect the environment? How they affect the ecosystem? So those are issues of concern as well. The other major thing which civil engineers do is to build our lanes of, they are responsible for our lanes of communication, particularly roads, railways, airports, right? So that building smart transportation systems is another major concern. And in that area, the new thrust is on multimodal transport. So that means if I want to go from point A to point B, right, I want to go in the most efficient way, in a way which requires least use of energy, and which of course gets me there in the fastest possible time, right? And to do that, I might want to use different modes of transport, right? I might want to use a combination of plane, train, car, and I want to do that in the most efficient way, right? So that is a major concern. And of course, when we build our roads, we are again using natural resources, whether our roads are concrete roads or they are made of bitumen, right? The resources that we use are of course obtained from nature. So we want to reduce our dependence on using virgin aggregates, right? Because aggregates are a constituent of concrete. Aggregates basically, if you are not aware, they are rocks, the broken rocks you see when people are building a concrete structure, right? Or when they're laying roads, right? So they're limited, our quarries are limited, right? And those resources, so we want to build green pavements. And finally, of course, environmental engineering, which is more directly related to our current concerns, right? So we want clean water, clean air, and we want to do that. We want to provide that for a growing population. And also, if possible, we want to recycle the waste we generate, travel, the structures we live and work, all of them have got something to do with civil engineering. So with that broad introduction, let me talk a little bit about structures, right? So building safer structures. The key objective is to produce a structure capable, when you want to build a safer structure, the key objective is to produce a structure capable of resisting applied loads without failure during its intended life. But it's a complicated task. But civil engineers nowadays, over the past 50 years, we have learned how to design earthquake-resistant structures. So the buildings we design can resist earthquakes of intermediate intensity with little damage. However, if you want to design a structure to resist earthquake forces, it can significantly increase the construction cost, right? And it is also true that even in the areas of highest earthquake risk, severe earthquakes occur only infrequently. The probability of occurrence of an earthquake is quite low. Does not make a lot of sense to design all our buildings to resist earthquakes of all possible magnitude, because the costs will be just too enormous, right? We cannot afford to do that. So we must make intelligent decisions, right? So for what earthquake load should I design a structure? That depends on several things. It depends, a probability-based analysis helps us to make intelligent decisions in this regard. It depends on the area we are building in. So the hazard, that earthquake hazard, the area is subject to, right? It depends on the fragility curves, the fragility of the structure, how susceptible the structure would be to an earthquake. How important is the structure? For instance, when I'm building a hospital building, right, I would want to make it resistant to a very earthquake of quite severe earthquake, because I don't want any damage to occur there, right? But if I'm building a domestic, simple domestic residence, single unit residential building, probably I do not have to make it so, of course, I should design it to prevent loss of life, but I do not have to design it in such a way that there is no damage at all, because otherwise the cost of building that residential building would become so high that it would become unaffordable, right? So these sort of decisions have to be taken into account, and that is why we use probability, and nowadays people use something known as performance-based design. Basically, you tailor your design. So when you're designing your building, you tailor it to ensure a desired probability of failure. It sounds a lot simpler than what it takes to do it, right? But it is an achievable goal, and people are doing it these days. Another key concept when you want to build safer structures is to ensure that your structure is sufficiently redundant, right? So that means when an earthquake strikes or a natural tornado strikes or there's an explosion, right? Yes, there can be some damage, right? But the structure should not collapse fully, right? So there should be sufficient load paths, sufficient redundancy built into the structure, so that although there is some local damage, some places of the structure are locally damaged, as you can see in this building after an earthquake damage, particular locations are damaged, but the building as such has not collapsed fully, right? So people inside the building are safe, and once the earthquake strikes, they can exit safely without loss of life or without if there's some important equipment inside the building, it will not be damaged permanently, things like that, right? However, you look at the picture on the right, this is a picture taken after the Bhuj earthquake early in the century in Bhuj in Gujarat, and it caused enormous devastation, right? Enormous devastation and loss of life, because the buildings there did not possess sufficient redundancy, right? They did not have sufficiently many alternative load paths, so that if one load path failed, it would still be able to transfer the weight of the building and the weight of the occupants to the ground safely without causing the collapse of the entire structure. And key to building structures with sufficient redundancy is to make our structures ductile. So what does ductile mean? Ductile means that, well, when there is an extreme load event, right, the structure will not fail, but it will deform, right? It may deform, right, but it will not fail, which is crucial to preventing extreme damage events. How can we build more ductile structures? We have to focus on the materials that we are going to build those structures with. So improved materials, improved concrete, improved steel, improved glass, which is being used increasingly these days, right? As well as fiber reinforced plastics, which are used for buildings as well, right? So it is desirable that the materials that we use for building should have high ductility. So subjected to high stresses, the material does not fail. It may deform, but it should not fail. It is also desirable that it should have higher strength as well. That means it should fail at very, very high stresses higher than the structure is possibly subjected to because of that loading. However, these are often two competing goals. So normally when we want to make our building or make our structure ductile, we have to sacrifice some strength, right? Because strength and very high strength often results in brittle behavior, right? So the structure will be brittle. It will fail rapidly when it exceeds a certain load level or a stress level, right? On the other hand, structures with comparatively lower strength show more ductility. So sometimes it is not possible to achieve both those goals. So we have to arrive at happy medium, right? But ductility is definitely more important than strength. Also, when we are trying to improve the materials that we will use for our structures, right? We want to make sure that the improvements that we do, we keep sustainability in mind, right? So those improvements should require, if we are using raw natural resources, maybe we can think of substitutes for them, and they should ensure that there is minimum additional consumption of energy, right? So the carbon footprint of our buildings reduce. So that is about structures. Next, I want to talk about water. As I told you right at the beginning, right? Because of this preoccupation and with global warming, right? We have to make sure that we can account for floods and droughts on a more regular basis, right? So this is going to place increasing demands on our reservoirs and dams. So how do we build our reservoirs and dams? We know that when we build a large dam, there is a cost, there is a price to pay. Land is flooded, right? Previously, land which was probably habitat or agricultural land, that is going to get flooded, right? And most importantly, building a large dam, it modifies the flow of water, right? The flow of water, the amount of sediment that gets deposited in the catchment area, right? So it modifies them in significant ways. An experience in our country itself, in our major hydel projects or hydroelectric projects, or for instance, the Damodar Valley Corporation, which was one of our first multi-purpose hydel projects, right? So the experience has been very mixed, right? So because those projects did not fully account at that time, they did not have the experience as well. They did not fully account for the long and short-term effects of those projects. So before we embark on building a large dam or a reservoir, we have to do integrated planning. We have to look into the short-term and long-term effects of the dam. How is it going to affect the environment? How is it going to affect the population? How is it going to affect the flow of water? And as you can see from this slide here, it's a very, very complicated process. There are so many competing considerations, right? And they're all interdependent. They're linked to each other, right? If you change one thing, the other is going to be affected. So you have to keep those things in mind. And it's it's a tedious, it's a complicated, it's a technically challenging process. But before we build any large dams these days, it is essential that we do these things, right? We undertake these studies, right? We do this environmental impact assessment. And civil engineers, right, they have a major role to play, right? There are other disciplines involved as well, but the crucial work is done by civil engineers, right? Particularly these things which I have circled in red, right? The factors related to the river and the water intake, geophysical factors. These are the areas where civil engineers have a major role to play. Transportation and networks, I already told you about green pavement technology, right? And I told you about multimodal transport, right? We want to devise transportation systems which uses the best combination of trains, planes, and maybe road transport. So if I want to go from, say I'm in Kharagpur, if I want to go from Kharagpur to say Pune, right? So how do I do that, right? So it will involve going, maybe there'll be a role for high-speed train, right? When I go from Kharagpur to Kolkata, and Kolkata to Mumbai, and from Mumbai to Pune, right? So that's from Mumbai to Pune, maybe I will take a high-speed train, right? from Kharagpur to Kolkata, maybe a high-speed train, and then from Kolkata to Mumbai, I might fly, right? Or if I want to go from Kolkata to Patna, for instance, or to Bhubaneswar, I might do the whole journey by high-speed train. If I want to go from Kolkata to Delhi, I might go to Patna by high-speed train and then take a flight to Delhi. So which is the most effective means of getting from point A to point B? And effective does not just mean taking the shortest amount of time, it means the mode of travel which has the least carbon footprint, right? Which uses the least amount of energy, which affects the environment in least. Another thing that I told you already about is green pavement technology. You know that most of our roads are built are built of bitumen, right? We have bituminous roads and we have concrete roads. Both concrete and bitumen are used natural resources. Bitumen is a byproduct from petroleum, right? So people want to find a substitute for bitumen obtained from petroleum. Bioasphalt, right, is a major research area where people want to use things like sugarcane residues, for instance, molasses, things like that, to produce bioasphalt. Or with the aggregates that we use for building roads, can we recycle those aggregates? Every few years, every 5-10 years, we have to renew our roads, right? So we have to dig up those roads, dig up the roads, and then we have those aggregates which were already there. Is it possible that we can use them again instead of breaking down a new mountainside in order to make our new road, right? Or when we are building a concrete pavement, right? Can we recycle the pavements? Can we recycle the aggregates that we have got from breaking down old buildings, right? So those are all concerns as well. And of course, finally, there is waste management and impact assessment. That is most direct, right? Its environmental impact is most direct. For instance, wastewater management, water and air pollution control, recycling and waste disposal. So nowadays there's a shift in emphasis, right? We are shifting from waste management to how to make waste do more for us, right? Generate electricity or heat from waste. Unfortunately, the way people do that, generate electricity from waste, it is not very efficient. Basically, they burn the waste. So most of them rely on combustion, which again is not good for the environment, right? So people are looking for alternative ways. How can we convert waste to electricity directly without burning, right? Without combustion. So that is an important research area, right? And then, of course, I told you about environmental impact assessment, which is becoming more and more important. Any major civil engineering project, before that, you have to do a thorough environmental impact assessment, right? To make sure that your carbon footprint is less. And in fact, if you do affect the environment adversely, how can you replenish? How can you mitigate, right? And how can you prevent or reduce the amount of adverse impact on the environment? So this is our usual waste to energy plant, right? You can see that it involves burning our waste and generating steam, which drives our turbine generator. And then whatever gases we have to screen out the harmful elements from those gases and then release. So it's a complicated and complex and expensive and not so environmentally friendly approach, right? So people are thinking of alternative approaches of using trash to generate energy. Okay, so what I've talked about now, up till now, I think I should have some time. I think I do, right? Okay, so I think I have at least another 20 minutes, 25 minutes. So in the next 20 or 25 minutes, yes.
I'm sorry to cut you in between, but actually due to the interest of time, we have to take some questions from the students and audience as well. So could
So
we?
another 15 minutes, would that be okay?
Actually, we don't have that because we have a follow-up session at 1:20
Okay.
itself. So can we like
Okay.
complete the theory within 5 minutes, and then we can continue the
In
discussion via
5 minutes?
Q&A
Okay.
Q&A session. We can
Sure.
conduct it.
Sure, we'll do that.
Thank you, sir.
Okay. Okay, no problem. So the quest for sustainability is driving our research, and so civil engineers need to be aware, right, of how to do sustainable design, the principles that underpin sustainable design. And once they link it with their engineering skills, right, which involves, your knowledge of mathematics, your knowledge of mechanics, your knowledge of solid mechanics, fluid mechanics, right? And if you want to specialize in environmental engineering, a fair bit of applied chemistry, right? So those are your engineering skills. And when you can link that with the principles of sustainable design, then it is possible to provide holistic solutions. Okay, and so then I wanted to talk about concrete, right? And I want to talk about in some detail, but in the interest of time, what I will do is I will give you a very, very brief introduction. So all of you are aware of concrete. It is the most widely used man-made material, right? And what is concrete? It is basically a composite of cement, water, aggregates, fine, what people normally call stone chips, right? Those are coarse aggregates, and then there are fine aggregates, which is sand, right? So like all composites, how you mix those constituents, right? How you prepare them, the conditions under which you prepare them, the temperature and humidity under which you lay your concrete, that is critical in determining how effective, how strong that concrete will be, right? And we have been using concrete since, almost times immemorial. If you know about the Pantheon in Rome, it was built around 125 AD, and the Burj Khalifa, which is the world's tallest building, I think it still is, they are all built of concrete. Now, the technology which went into building the Pantheon is very different from the technology which went into building Burj Khalifa, right? But surprisingly, over the past 2 decades, right, we have been borrowing, right? We have been borrowing many of the ideas which people had when they built the Pantheon, right? In our quest for concrete which is more sustainable. I hope I can get to that, right? So the main constituent of not the main constituent, it only comprises a very small percentage by weight, around 7 to 15%, but it is a very vital role. It has a very vital role to play because it is the binder, right? It basically binds the other constituents together, that is cement, right? Hydraulic cement. And the problem with cement is that it has a very large carbon footprint. Cement manufacture is responsible for only about 8% of the world's carbon dioxide emissions. So let me leave, and you can see why, because it takes around a temperature of 1400 degrees Celsius to produce clinker, which is the basic raw material for cement. So how do we make sustainable cement? So people, as I said, people are borrowing ideas which are now 2000 years old in their quest to replace cement. They're trying to use something known as geopolymers. If you think about the way people built the Pantheon, they did not have cement at that time. What they used was lime mortar, right? Basically, it was a pozzolanic material. And nowadays, when people are using geopolymers, right? Geopolymers as a replacement for cement, they're borrowing those same ideas, right? They're using pozzolanic materials, and then they're using alkali, right? They're dissolving them in alkali, and then if you dissolve a pozzolanic material in alkali, the resulting product possesses cementitious properties, right? So people are doing a lot of research in geopolymers as a replacement for cement. They're trying to replace coarse and fine aggregates, right? Coarse aggregates by using recycled aggregates if possible, sometimes artificial aggregates, and fine aggregates. Fine aggregates is mostly river sand. In most parts of our country, there's an acute shortage of river sand. So how do we get around that problem? So that is again a major research area. Okay. There are engineered cementitious composites. People have come up with this, where you do not need coarse aggregates. You do not need natural rocks at all, right? You get rid of natural. You do need sand still, right? You do need cement, but you don't need natural aggregates. And it turns out that what you replace that is with fibers, steel fibers, polypropylene fibers. They add ductility to the resulting composite. So engineered cementitious composites, And then compaction of concrete. So when you add all the constituents of concrete together, you have to compact. If you stay in an urban area, you should know that when there's a building being built next door, there's a lot of noise, and that noise comes from the mechanical vibrators in action, which are trying to compact the concrete. So people are trying to develop self-compacting concrete where you do not need vibrators, do not need mechanical vibrators. So it compacts under gravity, right? So that is an enormous saving, not only in terms of energy, it causes less noise, and it has many other benefits as well. Okay, and it allows us. So if you're building a skyscraper, you have a lot of reinforcements, a lot of congested reinforcement, and when you want to pour concrete in, and you want to ensure that concrete penetrates all the gaps between the reinforcement, right? You have to do a lot of vibration. On the other hand, if you have self-compacting concrete, if it compacts under its own weight, that is going to resolve all our problems with vibration. Okay, I think with this last slide, probably I will end. So there is a lot of interest in self-healing concrete, right? So concrete structures are liable to crack. If you're in a concrete building, if you go around and look carefully, I'm sure you will find cracks. Those cracks are not fatal cracks, right? They are part of the concrete. Concrete will have cracks. So long as those cracks are not critical, that is not a problem. But we also know that concrete can be self-healing, right? There are properties of concrete because the hydration reactions in concrete, they occur continuously. So a minor crack, maybe less than say 20 microns, it will automatically be healed. So nowadays people they are trying to use that idea in order to develop self-healing concrete, and one of the ways they do that is to use bacterial concrete, right? So they introduce bacteria in concrete, and those bacteria, they feed on if you provide sufficient material on which the bacteria can feed on, it generates calcium carbonate. And that calcium carbonate goes and deposits itself in the cracks within the concrete structure, and it sort of heals it, right? So that is again an important area of research. Okay, with that I will end, and I will go right to my conclusion, right? So these things we will drop for the moment, right? If any of you are interested, you will, and if you do study civil engineering, so you will learn about them. So use of sustainable materials is critical to the use of concrete as a structural material. So replacing cement is a major goal, and geopolymer cements offer a path forward. Replacing naturally occurring coarse and fine aggregates is another imperative. I say imperative because it is absolutely essential we do that. So recycled aggregates as well as engineered cementitious composites, they provide promising alternatives. Another thing which I did not have time to talk about is how do we improve the microstructure of concrete, right? In order to increase its strength, in order to increase its ductility, in order to increase its durability. And to sum up, right? So concrete is a highly versatile material, but we have to continually do research, improve its ductility, strength, and durability, and we have to find environmentally friendly substitutes to the existing ingredients in order to make sure that we can continue to build with concrete and steel and other building materials into the future. Okay, so thank you very much, and if you have any questions, I will be happy to answer.
So thank you so much for the insightful talk, Professor Deb. That was really nice. We have a few questions from the student side. And one of the most common one was, can you provide a general overview of the multidisciplinary elective courses in IIT, like even studying applied geology and materials in civil engineering itself?
Yeah, so we have an Applied Technology Development Center, right, which is a forum for but also in our regular programs nowadays for our dual degree programs. So I believe most of those who are asking this question are undergraduates. So in our dual degree program, we have introduced, and that is from the 2021 academic year. So if somebody does a BTech in civil engineering, it is quite possible for him to do a dual degree in, say, material science, or for instance in artificial intelligence. So the final year in the five-year course, they will take courses or maybe even in financial engineering. So that is the best medium for doing interdisciplinary dual degree, is the best medium for doing this sort of thing, I think. And it is very much possible.
Well, thank you for the answer, Professor Deb. We could discuss a great detail, but in the interest of time, we will have to end the session here. So once again, a big thank you, Aragya sir, for taking out precious time from your busy schedules and serving the students with your knowledge. And I hope everyone got a great insight from this. Thank you for having, and it was a pleasure having with you.
Thank you very much. Thank you for listening and having me. Thank you.
Thank you. Have a nice day. And for all
Bye.
the students there, we have another session which can be accessed at 1:30 p.m. So please do join for that.